So this is the second video where we are going to discuss about the absorptions and the scattering of the radiation. First video was on the almost the basics of the radiation and what happened when radiation moves through a cross-section area and all that stuff. So today's video is going to be an absorption and a scattering. First of all, why this is important? Because when we study the atmosphere of the stars, what we see is that when there is some sort of radiation coming into the medium and entering into the medium, what will happen is that the radiation suffers from the absorptions, scattering, and re-emission of all of the radiation. So to study all these, that how some sort of radiation, radiant energy which is flowing into some sort of surfaces, and how we can govern this with some sort of equations, and that's the motto of our this particular lecture series, learning of the transfer equations and the solution of the transfer equations. Because the transfer equations will tell us about the how we can govern the intensity of the radiation that is coming out after moving through some sort of medium. When there is an absorption, scattering, and also the re-emissions of the radiation. So this is the second part. And first of all, let's understand that suppose that you have a radiation whose intensity is IV. Suppose that it passes through some sort of medium. So let's say I have drawn some sort of medium like a cylinder. So this is purely imaginary situation. And this particular enters into that particular radiation, enters into this particular cylinder. So what will happen is that there will be change in the radiation by a small amount. So we have to calculate this particular thing. So it is a very important formula for this, that how we can govern the change in the radiation intensity of our radiation. So this can be written as minus K rho I V and ds. So this is our particular formula which tells us about that how much radiation is being absorbed in a medium. Here K is the absorption coefficient, or more efficiently mass absorption coefficient. Here rho is the density of the material and ds is the thickness of the material. But how thick is the material? So in this particular scenario, you can say that this amount of radiation is being absorbed. But the fact is that it's not always true that if there is some sort of intensity, or you can some sort of radiation which is going into the material, and all of that particular energy, or you can say that some sort of intensity is being absorbed. What will happen is that you can also say that the energy which is sent, which was missing, can be redirected and can be scattered. The main motto of my point was that to understand that whenever there is a decrease in this particular intensity of the radiation, it's not always true that the radiation is being absorbed. The fact is that maybe the radiation is scattered in all direction. You have to just measure the radiation in all direction, and you will just sum it up. You will find out that yes, no radiation is being absorbed, and this is called a true scattering, a perfect scattering of the radiation. Perfect scattering. Okay. So now we try to do this with some sort of mathematical steps. So we are going to decide this perfect scattering into the mathematics. So let's define the scattering of radiation. Okay. Okay. So suppose that you have radiation. I will define, so for scattering, let's say I defined a coefficient K mu, which is the scattering coefficient. Scattering coefficient. And now if I imagine a pencil of radiation which is going into our, let's define a pencil of radiation which is going into the dm mass, frequency d mu, and with the solid angle d omega. And how can we define this as scattering radiation? The perfect formula is like k, k mu, and here it was rho. I is the radiation intensity, and here it will be ds, multiplying it with your this particular term which we have studied in the previous class, which is I mu cos theta d mu d phi and dt. Okay, so let me just put it in a, this is very important. Here I think I have not included the correct term. Here it should be not dt, here it should be d sigma, which is a surface element. So this is how we define the scattering of the radiation. So this is a quite big formula. So let's study that what exactly all the terms are. So this is nothing, it's just the radiation intensity. This is theta term, this is the frequency, this is the omega, which is your solid angle, this is your d sigma, which defines the surface area, and rest of the term you all know about that particular thing. Okay, so now if we carefully see that how we define the dm mass, because this radiation is moving into a dm mass of cross-sectional area d sigma. So dm mass is defined as rho into rho into cos theta into d sigma into ds. So this is how we define the dm mass, and if you plug down the value of here, you will get this particular term as k mu, and rho cos theta will term will not here will be visible, and the term will be I mu. ds will be also not there, cos theta will also not there, it will be d mu, and here it will be d phi, and finally dm. So this is how we define the scattered radiation. So this is how we define the scattered radiation. Sorry for the bad writing. Okay. So this is how we define the scattered radiation. But the fact is that the radiation is also scattered in all of this particular direction, all direction, not on particular straight direction. So we have to also define an angular distribution of the scattering of radiation. So for this, now the important part is here, which is a phase function. This is your phase, 1 minute. This is your phase function. This is very important because the formula here that I have written is not complete. Why it's not complete? I'm going to tell you this very thing here. Phase function. What this is and what's its sign. So generally the phase function is represented at p cos. Let's say I gave it some another name as let's say theta. Please don't confuse it with this particular theta that appeared in the previous equation. This is just this particular theta. I'm going to tell you what is it. So what's phase functions? The fact is that the radiation that is scattered will not scattered in only a particular direction, scattered in all of this particular direction. So to measure and to know about the scattered radiation of its angular distribution, it means to know about the angular distribution of the scattered radiation, we define this particular phase function. So how we are going to use this in this particular equation? So we are going to use this phase function in this particular equation, and let's see what will happen. So when you apply this particular phase function in this particular equation, you have to just multiply it p cos theta, where theta is different angle. Okay, I'm going to tell you that what exactly this theta is, and multiplied it with this particular equation, which will yields us k mu I mu and d mu d omega, and finally here what thing is missing, dm. Okay, and here dm. So this is how we are going to, but one more term we are going to add, which is multiplied by d phi by 4 pi. So as you can see that here I've added one more extra. So you have to understand that these two solid angles are different. This particular solid angle is for the incoming radiation, and this is the solid angle for the scattered radiation that is scattered. And this particular theta is also special meaning. So let's say we have some radiation which is moving in this particular direction and it's scattered in this particular direction. So theta is the measure that how at what angle this particular radiation is being scattered from your previously solid angle. So that is the meaning of this particular theta angle. So suppose that you have some radiation in this particular direction having an angle, a solid angle d omega, and if you want to know about that, what's it's the scattered radiation. So this scattered, if there is a radiation which is scattered at an angle theta, this theta is measured from the solid angle of the incident radiation, and that's why it's called the angular distribution of the intensity radiation, angular distribution of the scattering of radiation. And this whole formula gives us as the rate. What rate? The rate at which at how many radiation is scattered. And this particular term p cos theta is very important because this is a phase function, and this is also very important. And collectively you can write out that p cos theta into d phi dash divided by 4 pi integration is nothing, it gives you the probability of the radiation that is the radiation is scattered in that particular direction, in which direction, this gives us the probability. And in this particular case, if this probability is 1, it means the radiation is scattered in all directions. Maybe this can be less than 1. That's why we define p cos theta equal to omega naught, where omega naught is some different types of quantities, which depends. It means if there is pure scattering, it means there is no loss of energy. So when there is no loss of energy, no loss of energy, this particular omega naught equals to 1. This signifies that there is no any loss of energy when the intensity, when there is a scattering of the radiation. But yes, this can be less than 1. So in the case when there is also absorption plus a scattering, then this omega naught value, then this omega naught value, and 1 will be greater than equal to this. This equality will hold when there is also absorption plus a scattering. But when there is pure scattering, which is perfect scattering, this p cos theta will be 1, and when you do the whole integration, the probability will come out to be 1. And when you this is 1, this whole equation becomes what equation for the perfect scattering. So when there is perfect scattering, it means that you can't generally tell that from which direction radiation. So it's not the fact. The meaning is that you can't tell that from which direction radiation is coming, and this is called the isotropic radiation, and it is in the form of the perfect scattering. It means when there is a perfect scattering, there is an isotropic radiation. Maybe the value of omega naught is less than 1, and that signifies that there's some sort of absorption of the radiation. So this is about how we define the angular distribution of the radiation when the uh, radiation is being scattered in all directions, and if the probability is equals to 1, it is the case when there happens a perfect scattering. It likes there is no loss of energy, like the conservation of energy laws in the you can take the analogy from the conservation of energy law in the dynamic systems, that is here, that there is no loss of energy and omega naught is equals to 1. But yes, omega naught can be, you have to remember that this equality not hold when you are discussing about true absorption plus true spotting. It means the combinations of the absorption and the scattering of the radiation. This is how much radiation is going to be scattered and how much radiation is going to be absorbed. This phase function is also very important because this defines us generally the rules. So this is the basic meaning of the phase function and how it defines the scattering of the radiation and when the scattered radiation and this phase function will equal to 1. From this definition, you can also tell that this omega naught is nothing, it's an albedo of the radiation. What is albedo? So albedo is a fraction of the radiation which is being present after the scattering. And 1 minus omega naught will tell you that how much radiation is being absorbed. Or wasted, you can say that, not waste, but you can say that it's absorbed. But in this case, when omega naught is equals to 1, you can see that this particular equation goes to 0. It means no any absorption occurs and there is a whole perfect scattering scenario. And the fact is that this phase functions can also take the values of the formula, which I don't remember, and it's also not in our case, and you don't have to study those higher things. So for in this particular video, we only have to study that what is this phase function, basic meaning of phase function, because it defines the angular distribution of your radiation and stuffs. When this p cos theta is equals to omega naught is equals to 1, it means that is perfect scattering. And when it less than 1, then it means there is an absorption plus scattering. This is my whole video on understanding about the radiations, scattering, and all that stuff, that how it define the scattering and perfect scattering. Next video is going to be on the emission and more detail about the absorption coefficients and to finally derive the transfer equations. So this is for today's video. Thank you for watching my video.